So welcome to the session. So in this video, we will look after the Brayton cycle. So it is also nothing but a Joule cycle. So Brayton cycle is a standard ideal cycle where the application is the gas turbine. So in this unit, we will be cover the Otto cycle and diesel cycle, dual cycle, and Brayton cycle. So here you can see the during the thermodynamic cycle of operation, there are four thermodynamic process involved. So if you see in Otto cycle, you are taking 1 to 2 as an isentropic compression, and 2 to 3 is the constant volume heat addition, and 3 to 4 again expansion, and 4 to 1 is the constant volume heat rejection. So here also we need to operate these four operations for thermodynamic process, which will be taken as a consider as a whole system. So here also the working fluid is taken as air. So where the specific heats are taken as a constant values. So in the side stand cycle, this is the layout. So first one is the compressor. So where the air is to get compressed. So here the two observation is there are two heat exchangers will be taken. So in this heat exchanger, heat is to be added in the form of Q1, and later on there is a turbine used to rotate the shaft, so which will the compression turbine will be lies on same single shaft you can see here. So and again 4 to 1 is there should be some rejection. So according to thermodynamics there is a source and sink, so you can see here Q1 and Q2. So these are high temperature source and low temperature sink. So in this breakdown, these gas turbines will be an important application. So we need to go to identify the efficiencies for Brayton. So here you can see this is a closed cycle gas turbine engine where TS and PV were given here. So 1 to 2 there is an isentropic compression. So reversible adiabatic compression. So here entropy will become constant. Okay. So under this compression, you can see there is a slight raising of pressure with respect to temperature. So the compression volume, so you can see V1 and V2. There is a it is not a constant volume, it is a isentropic compression. There is a volume change. So you can see there is an isobar. So here under particular pressure we need to add some heat. So we need to supply some heat at 2 to 3 where a peak pressure will be maintained under 2 to 3 process. So we have to identify the volumes also with respect to V1, V2 and V3, and you can see constant pressure heat addition MCP delta T. So here the next 3 to 4, 3 to 4 you can see here there is a working device, it is called turbine. So turbine is an application and it is mounted on a single shaft where compression turbine lies on the single shaft. So you can see PV power of gamma is equal to C reversible adiabatics from for 1 to 2 and 3 to 4. So here it is work done by turbine, so that is expansion device. So after reaching 4 to 1 there should be some heat rejection to the surroundings, so that is QR. So it is also under constant pressure. So see, you can see the 4 and 1, P1 is equal to P4. There P3 is equal to P2. So under these pressures, we need to follow this particular constant pressure heat reaction. And you all know that thermal efficiency for any cycle is net work done by heat supplied or heat input. So we will rewrite this 1 minus So Q in minus Q out, it will be rewritten as like this. So here energies need to be identified. So energy inlet and energy outlet. So here we can follow this energy conservation and standard flow energy equations. Okay, and we will like net half mv square and mg z. So we will follow the mass flow rate at 2 to 3. So why it is 2 to 3? Why? Because here in a heat exchanger where mass will be entered and mass should be leave out before going to the turbine. So here Q1 is in the form of by um, introducing or by using some mixture of fuel, homogeneous mixture of fuel where it undergone combustion. So the gases which used to rotate this turbine. Okay, so generally this is the working model. So you can see here the specific heats as given, and the new term is called enthalpies. So enthalpy should be taken as a property. So delta H will be written as H3 minus H2. So after combustion, the temperatures will be huge. The enthalpy, the amount of energy which is stored in the gas. So gas mixture. So we need to rewrite this. So already we have seen the another gas exchanger, heat exchanger under 4 to 1. So there should be some enthalpy difference MCPT. You can see here H1 and H4 will be having higher enthalpies. And here one thing, H is a function of temperature. You all know. So that's why they have rewritten H in the terms of temperature. So there is MCPT delta T. So by substituting Q in and Q out in this particular thermal efficiency, you will get 1 minus so CP under constant pressure heat rejection, the value is same. So Q out, Q in. So substituting these two, okay, you will get in the temperature ratios. So we need to convert into not volume here pressure ratios RP. So T2 by T1 is equal to P2 by P1. So directly proportional. And under this adiabatic reversibility gamma minus 1 by gamma for the gas turbines. So you can see you can substitute these values in this particular T1 by T2 is equal to 1 by pressure ratios is P2 by P1 RP. So here we need to interchange the limits, temperature limits. Okay, so that's why you're given 1 by. So finally, the efficiency of Brayton by using this RP P2 by P1. In Otto cycle, it is RC compression ratio. Here it is pressure ratio. So 1 minus 1 by pressure ratio whole power of gamma minus 1 by gamma is the efficiency of Brayton. So in next topic we will see the what is the working of four-stroke petrol engine. Thank you.